So this is the fourth presentation in the series on mineral processing analysis. The first was an overview of the other three. Of those three, the first was creating particle types from flotation data. The second one was working out the kinetic flotation rates. And the third one is doing simulation, which is this one. As always, this is an overview. We're not going into depth. If you want to go into depth, either have a direct course or I'll be providing in due course online courses. Now, this model is simple. Treat it as schematic, just getting an overview of how to do simulation in Excel. So my company is Midas Tech. My name's Stephen Raywood, and I've developed a flowchart simulation system in Excel. It's called ExcelFlow. Now, this methodology isn't entirely new. There are other flowchart simulation systems available. One of the most successful is LIM by David Wiseman, specifically developed for mineral processing. But there's various differences between LIM and ExcelFlow. And having said that, I'm certainly happy to see later compatibility between the two systems. But ExcelFlow is a flexible system. Models can be written in front-end Excel, so you don't have to be an expert in VBA to incorporate models. If you do wish to add a model using VBA, or VBA is Visual Basic for applications, if you want to write your own code as a model, that's okay, you can do that as well. But in this particular presentation, we're focusing on people who use front-end Excel. As again, it's holistic. I don't go into much detail. Now, ExcelFlow, when I developed it, I didn't want to specifically limit it to mineral processing. So it's more of a framework, and it's largely a process modeling in Excel. So it can be applied to any process that can be represented by a flowchart or a flow sheet. Mineral processors tend to say flow sheet, whereas business modelers tend to say flowchart. So it can be used for applications such as mineral processing, which is where I get most traction, and it can be used for, say, electrical circuits or indeed water flow in pipe. But of course, in this overview, I'm focusing on mineral processing. So why have I created this system? Good question. I developed it largely because I developed my own models in mineral processing originally, and my attempts to get my models incorporated into other existing systems didn't gain appropriate traction. Some models went into JK SimMet and JK SimFloat, but apart from that, I haven't really integrated my models in any software. But I also wanted to use it as the basis for education courses. So once someone grasps ExcelFlow, they can easily learn other process modeling applications such as electrical circuits, systems engineering, civil engineering, even mechanics, and of course, financial modeling, business process modeling. Because the alternative is largely MATLAB. And MATLAB is a really good system, very cheap if you're at university, but once you get out of university, it's very expensive. So here we see the mineral processing circuit that I'm aiming to simulate. These are cleaners, and if you looked at video 3, which was model fitting, it gave us the flotation rates at each of these units. So they're inputted into the simulation system, and it has various recycles, and we have a con and we have a tail. Now, just to give you a slight digression, I could have inputted into it an electrical system as well. Now, it's important to understand that these type of flowcharts can be constructed in Excel. Now, this particular unit is not a cyclone. It's simply used to indicate the fact that two streams are combined, because the way you use Excel and the way it would work here is you would get a recycle, and in an Excel you would get a circular error, and these sums are used to stop circular errors. Again, that'll be explained in more detail in the more detailed course. This slide shows the circuit that we're simulating. This is created using the flowsheet capability in Excel. So I'd recommend you do the course Flowcharting in Excel in Udemy. So ExcelFlow has three types of users. The developers, who might say, I want to use ExcelFlow and create a customized system for electrical engineering. So they incorporate models, they might even make up their icons. Then we have designers. Designers effectively take an existing version of ExcelFlow and create a specific application, such as a simulation for a mineral processing circuit. An end user is the person who runs it, and they make minimal changes, such as the feeds, and they run it and they see results. Here we see an outline of the various types of users of ExcelFlow. There'll be a domain expert, such as an electrical engineer or a mineral processing engineer, who tries to or incorporates the models. The designer takes the models and visually creates the system by drawing a flowchart. The end user simply runs it, and he may make minor changes such as input. And as you can see, we have a very happy end user. The method basically means that you create a template for each unit model. So for the flotation cell, there's just one Excel template which represents flotation cells. The icon in a flowsheet is then associated with the corresponding unit template and connectors in mineral processing streams. ExcelFlow, basically a visual programming system that from the flowchart determines how connectors and units are related. It takes a unit template and creates unit models for each particular icon. That's the basis of the simulation. It's very straightforward. So I haven't here gone into the details of creating a template. Again, that would be part of the more in-depth course. But a good starting point is to do my Udemy course on formatting in Excel. Create a flowchart. Again, there's a Udemy course, flowcharting in Excel. Then I have various add-ins, quite a lot. And these are used to create ore stream and unit information in Excel using the information from the flowchart and the templates. The end user, he might add specific knowledge about the unit operation or feed to the circuit. So in the case of flotation, he might change the kinetic rates, he might change the feed, and then he simulates. In this particular case, the flotation model is simplistic, just recovery. Going to the concentrate is this function here in terms of the kinetic rate and the residence time, but we don't have the residence time, so K times T is a combined value. So when we simulate the plant, we get the information blocks which show how effectively the particles are being separated. Now this is a bit hard to read, so I'm just going to focus on the three information blocks that are most relevant. So we have the feed, tail, and the final con, and we see that the lead has been concentrated in the final con. And we can, of course, adjust the flow sheet, we can adjust the inputs, and we can resimulate. So again, if you want to know more information, let me know, and that will prioritize providing courses. Thank you for your attendance and interest.